Before I actually introduce the speaker, I would like to say he's from Cornell. And I would like to interject that Cornell is a great place for anyone interested in logic, mathematics, computer science. Professor Robert Constable.
Well, let's see. We'll try out microphones. This one working? Yes. Yeah. All right, good. So thank you, Gerald. And I should mention that one of my former students, Wojtek Mozlowski, who won the Sachs Prize, is here in the audience for his PhD thesis at Cornell. I won't be talking directly about that, and I will be talking about intersection types, which is the title, I guess, but under a different title and with a different purpose. This was at the suggestion of Anil, who wanted me to present a more general topic. So there's the title, and let's see if we can get this thing to work here. Yeah, and that's the abstract that I thought you were going to read, but you shouldn't read it now. I've got a narrative that I'll tell you about. That's saying something like, I can't actually read it, well, let me get onto my
screen.
Yeah, I can look at
looking at your own screen is better.
Yeah, that's for sure. Okay. Anyway, that was the abstract that I sent in about this talk, and really you can see in there that I'm going to be speaking about first-order logic and completeness of intuitionistic first-order logic with respect to its intended semantics, a title that I got from Sergei's paper on this subject. So the link to Sergei's work is that in 1999, when he was at Cornell, he wrote this paper on uniform provability realization of intuitionistic logic. And he was using proof logic, the logic of provability for this. And here's the narrative theme of the talk. This will give you the idea of the story, and then we'll go down into some details. I've never actually tried to lecture about this result before, except briefly at Tel Aviv University. So Arnon has heard me try to state this result before. So here's the narrative, the way I see it. So first order logic is certainly a central notion in logic, no matter how you approach it, from mathematics, philosophy, or computer science. And it comes in at least these three flavors. There's minimal first-order logic, intuitionistic first-order logic, and then the full classical thing. And those are increasingly expressive theories. Well, on one interpretation, if you're a classical mathematician, if you're a constructive mathematician, then the first two show increasing expressiveness, and the last one falls off a cliff there. But in classical logic, Gödel's completeness theorem ties together the proof theory and validity, and it's central to the study of first-order logic. We teach that probably in every course on logic. And the interesting thing is, though, that you can't actually give completeness theorem of that kind with respect to the intended semantics for first-order logic, which I'm calling the Brouwer-Heiting-Kolmogorov semantics. The only completeness results we have are for Beth and Kripke models and that sort of semantics. Now you could say, well, who cares whether you've got a semantics for minimal first order and intuitionistic first order logic. It's interesting to a small bunch of oddballs who live in Manhattan and Ithaca and a few other places. But the situation has actually changed quite a bit with the engagement of computer scientists in using constructive logics for formal methods and for verifying computer systems, in particular in computer security. So now literally hundreds of people a year learn constructive logic out of the Koch theorem prover. It's being very widely used around the world. And they also get it from Agda, which is a theorem prover in Sweden that's based on Martin-Löf type theory. They get it from Minlog, Helmut Fichtenberg's really elegant implementation of Minlog, from NuPerl, and from Meta-Perl. And we have some of the creators of Meta-Perl in the audience here. Alexei Nogin is one of the principals in that system. All of these are based on constructive logic. And it turns out that constructive logic is taught routinely in courses like advanced programming languages at Cornell, because the idea of propositions as types and proofs as programs has now become integral to the way we look at programming languages. So the problem is we get our colleagues and our students all excited about the value of constructive logic. Then they start reading logic books, and I probably have 40 copies of Smullyan's first order logic book, this classic, absolutely beautiful book, lying around all over the department. So people pick them up, because I've been teaching out of that for, I don't know, 20 years. So there are hundreds of copies around. And they see the completeness theorem there. It's so beautiful. And they say, well, what's the completeness theorem for intuitionistic first order logic? And then you have to tell them, well, you've got to know about Bet models or Kripke models, and by the way, those aren't faithful to all what we taught you. It's not the semantics we've been using. And they really get confused and upset, actually, about this. They say, what's the matter with you guys? If this semantics is so important, if it's the intended semantics, and we've got all these brilliant logicians in the world, why haven't they figured this out? So here's what happens, continuing the narrative. We've got this intended semantics that goes under many names, by the way. It takes my colleagues a long time to figure out which semantics they should be talking about, because the logicians, you guys, call it BHK. And computer scientists didn't like that. So they called it the Curry-Howard isomorphism for reasons that are easy to explain historically. That's out of certain pages in Curry and Fay's book from 1958. And the computer scientists know the pages, 312 to like 316. There's the isomorphism. Okay, so why did they pick that word instead of, say, BKH semantics or Martin-Löf's term, propositions as types, or the term I like, because I was associated with that, proofs as programs? Why not these things? Or correct by construction programming, which, by the way, we just came from a DARPA meeting, and that, under that banner, there were several talks where they're applying this method of correct by construction programming. Or it could be called realizability semantics, as that's how they speak about it in France. Okay, so anyway, why isn't there such a semantics? Well, okay, so what else did I say? Okay, so the one reason is since 1947, when Bet suggested that there would be a completeness proof along these lines using BHK semantics, people have not been able to find it. Bet turned to his Bet models, and then Kripke simplified them. They just couldn't find a completeness result. And it's because they were using, well, they tried to use intuitionistic validity. And that's a very sensible notion. If you read Troelstra and Van Dalen, they say, well, look, we'll just use the analog of what happens in classical logic. We'll say validity means that the formula is true with respect to any model and any interpretation of the relations over that model. So that's intuitionistic validity. Well, one problem is there's some vagueness in there. When you read Troelstra and Van Dalen, they say, well, that all sounds good, but what is a domain? So I don't ever ask my colleagues to read that, because they say right away, well, we're not sure what the domain is. Should it have free choice sequences? Should it be this? Should it be that? So there's vagueness. So already you get a little uneasy. Wow, they don't even know what the domain is that they're quantifying over. And then they say, and now the relations, we don't know whether they should be total or partial relations, but anyway, there's this notion call intuitionistic validity. And basically, all we know about it is are negative results. Let's say Kreisel, for example, showed that if you accept Church's thesis, then the intuitionistically valid formulas are not recursively enumerable. So you're not going to get completeness. Furthermore, Kreisel showed back in 1970 that completeness under intuitionistic validity implies Markov's principle. So these are somewhat negative results. And you think, well, okay, we're not going to be able to go down that track. And indeed, I thought about it once we adopted, well, once the world that I live in, the computer science world, started to converge around first intuitionistic type theory a la Martin Löf from roughly 1972, but modified until 1984. And then at Cornell, we adopted that basic idea, the Martin Löf semantics, and built what we called constructive type theory and implemented it in the new Perl proof assistant, in the Meta-Perl proof assistant. And there we could make definite what intuitionistic validity is anyway. We could say, all right, the domains are types in this type theory, and the relations are relations over those types. So we had a very definite semantics, but nevertheless, we couldn't get a completeness proof. A bunch of us looked at that, couldn't do it. So what happened recently, just in the last 3 years, is that we discovered another notion of validity that seems pretty natural, that is very natural. We call this uniform validity. And it's something that Lauckley was trying to find all the way back in 1969. He did work on intuitionistic propositional logic, trying to do completeness. And he said, what's missing from the BHK semantics is some kind of uniformity. And he tried to capture that using permutation semantics. But that didn't work out for him. But we noticed, and partly because of people in this room, Alexei Nogin was a key player in this, we started to notice that we should be putting a new kind of logical operator into constructive type theory, and that is an operator based on the intersection type. I won't talk too much about it, but at Dexter's Festschrift a couple of weeks ago in Ithaca, there was a stunning talk about the power of intersection types, and I should just repeat that result by Yakov Rohoff. He started off his talk there at Dexter's meeting by saying, look, if you're trying to decide the inhabitation problem or the validity problem for the simply typed lambda calculus, you've got a p-space complete problem there, which is sort of tractable in a way, polynomial time, polynomial space, exponential time. If you add the intersection operator as a logical operator to that theory, it becomes undecidable. So you go blam, all the way out of this world from just that one type constructor. So it's a very powerful thing. I wouldn't have reacted the same way that I did to that talk a few weeks ago had we not been studying this intersection type for many years. So the punchline goes like this. Once you can express uniform validity using an intersection operator that I'll talk about, you notice that all of the proofs in intuitionistic first-order logic create realizers. We could call them Brouwer realizers. They don't require Kleene realizability. You don't have to arithmetize things, but you get these Brouwer realizers. And if you've got the idea of uniformity from the intersection type, you see that they're all uniformly true. So you realize, well, you're not going to get a completeness theorem unless you've captured uniform validity. So that's what we did, because it was in our theory already. We had this thanks to Alexei and Jason Hickey and Alexei Kopolov. Those three guys, with my eager participation, I got a result here and there, but they were really into this, and they said these theories have to have those new type constructors, even though they weren't standard operators. And later in the talk, I'll give you just a quick survey of some of the results they were producing that convinced me. I was very conservative at first about these, but they just overwhelmed me with results, saying this has to be in the theory. And the benefit of it is that you can now prove a very simple completeness theorem. That's not on the slide yet, but it will be there. So that completeness theorem I'm going to talk about, I won't try to prove it, but state it and give you the sketch of how it goes. The completeness theorem is this. A formula of intuitionistic first-order logic is provable if and only if it's uniformly valid. So there you've got a real tight result. If you use uniform validity, first you see that all the provable formulas, they are uniformly valid. And then the hard bit is the completeness theorem, where you show, all right, let's look at uniform validity over this type theory with the intersection types and see if we can get to completeness there. And it took my colleague Mark Bickford and me about 1.5 years to actually work this out. So I won't be able to show you the proof, although it's in an archive paper. We've got it all written down. It's being refereed at the moment. So here's the lecture plan. I'll very briefly review the BKH semantics, and you guys could, by nodding your head, say, like, we know all this stuff, just keep going. Then I'll examine the constructive type theory and stress these results since 2000 on the intersection type and the union type that goes with it. Then I'll define the formal semantics for intuitionistic first-order logic and have to stress the case of minimal logic. You have to do the completeness theorem first for minimal logic, and then you use Friedman's embedding of intuitionistic logic into minimal logic to get completeness for the intuitionistic case. Okay, and then I'll state the theorem and give an example of it. Time permitting, I'll discuss the partial functions. There's part of our result that requires these, what I like to call constructive domain theory, what Dana Scott was doing in the 70s and 80s. He was building up this domain theory, and he didn't do it constructively, but it can be done that way, and we had to use a little bit of that stuff. So if there's time, I'll mention those results. Okay, so here's a quick introduction to BKH semantics, and I assume like everybody knows this. You could nod your heads if you think, yeah, this is going to be boring. Oh, okay, so I'll just say this very quickly.
Not to me, I'm not bored.
Okay, so Gerald is not bored out. All right, so here's how we interpret statements of predicate logic intuitionistically. For the atomic predicates to assert them, or in Kolmogorov's terminology, if you think of the predicate as a problem, to solve that problem means to provide some kind of evidence, lowercase p, in the parameters of the proposition, which shows that it's true, or that the type it represents, the type of all the evidence for it, is non-empty. To assert, if you've got now some predicates, atomic or in general, two predicates P and Q, to assert them in the following formats, to say P and Q means that we have evidence, little p, and evidence, little q, for those propositions P and Q. Some people like to refer to that evidence as proofs, right? You have proofs P and Q, but if you do that, it complicates the theory. You want a semantic theory, and you can separate evidence from proofs. You can give a semantic account of evidence here. So, and we'll see in detail what the evidence is as we go along. Now here's the thing. To prove P or Q means you have evidence for either P or Q, and you know what the evidence is. It's tagged. This is the evidence for P, this is the evidence for Q. So if you prove P or Q, you know which one you proved. Okay, to prove, whoa, what happened there? It's a funny looking symbol. Huh. It's interesting. That I don't even know what that was supposed to be. Let's say, oh, that's supposed to be implication. Yeah.
Did you embed your fonts?
I do have this in PDF, so we could switch to it. If it gets really bad, I could. Anyway, that's P implies Q. To know P implies Q means that there is an effective procedure F that takes evidence for P and computes evidence for Q. Not P means there's no evidence for P. Another interpretation of not P is P implies false. So if there were evidence for P, there'd be evidence for false. And the quote operator there, yes, for all X of type A in the domain A, for all XP means we have an effective procedure that takes any element of the domain A or the type A and computes evidence for P of A. And the $sign operator, what the heck was that? Oh, that's the existential quantifier. Let's see.
Of course, don't really consider
Yeah. So I didn't go ahead and check these slides because I brought a PDF. I should have checked them while I was socializing with people up here. But let's see. Maybe it's not going to be so bad. Let's look on the next. Oh boy, it's going to be worse. Oh, it's going to be. But we got the existential quantifier. I wonder if I should switch. Well, I don't know. Let's see how it goes. I could switch to the PDFs, but should I do that?
Yeah, sure.
Okay. You know how to get that to happen? Yeah. So while we're doing that, does anybody have a question yet? You might have one.
Well, it's the usual. It's the usual thing about. Aha.
Oh, we didn't copy that. Yeah. Okay. So we didn't copy that. Thank you. Yeah.
I mean, you have the various equivalents there. I mean, assertions there's no evidence, or this converts this to this. There's the usual issue about in what kind of framework do you know that those facts are, and what framework they're to be considered.
Right. So that's a very critical question, and the answer is we're using the framework of constructive type theories, this CTT. So that's what's making everything precise, and that's what makes the problem precise, but also very hard, because now the evidence can use arbitrary types, can use anything from constructive type theory to show you that the thing is true. So that's like in model theory, right? So when you're doing validity, you can use all of the set theoretic world to show that a formula is valid. So we're in that same world here now, and we say, okay, we're going to use constructive type theory. Oh, wow, that was a lot better. Thank you.
I like that better, by the way.
Yeah, this, okay. So now we can read what's going on here. And the question was very pertinent. That point should be very clear. So to prove P implies Q means that we have an effective procedure in this constructive type theory. You can actually write down a computer program or a lambda term or something that takes evidence for P. So that's something that, again, evidence in the type theory. It's a real mathematical object, constructive mathematical object, and we'll convert that into evidence for Q. And we teach this to undergraduates at Cornell, and they get this interpretation of implication right away. You know, when you try to teach them not P or Q, they really wonder. But here they say, oh yeah, that's what we have to do. And of course, we teach all these results in complexity theory that say if the extended Riemann hypothesis is true, then the SAT problem is solvable in polynomial time. Now, in neither case, you don't know whether the Riemann hypothesis is true, and you don't know whether SAT's P time. And they know this. They see, well, we don't have the truth value of either side, but that implication makes sense to them. We're taking the evidence for the Riemann hypothesis, and over a long period of time, we get evidence for SAT being polynomial time. Okay.
You're not claiming that result, though, are you?
Pardon? That is a result. That's a theorem, but we don't. We prove. Dexter proves that result. Probably. Did you prove that in your complexity class?
I think I proved something about a guy eating ham sandwiches or something.
All right. Anyway, here's how, now once you've got that intuitive idea, you can put this into type theory in a very straightforward way. And interestingly enough, now this PowerPoint thing didn't take the brackets there. Those are supposed to have square brackets around them, so that's really weird. Anyway, if we had brackets around that, and I could put it over there on the board, but I think I shouldn't take too much more time on this. Those brackets are saying the semantic bracket around A and B would say the interpretation of it is to take the Cartesian product of the evidence sets for A and B. For the disjoint union, for the OR, you take the disjoint union of the evidence sets, and so forth. And so again, that's very weird that I didn't get those fonts. Anyway, it's been well known for a while that you could apply this evidence semantics in a classical setting too if you use some kind of generalized computability. You talk about computing with respect to an oracle, then you can show that from a classical point of view, this semantics agrees with Tarski's semantics. So I wrote a paper on that a long time ago in 1982 called The Semantics of Evidence. And it's a nice, very classical paper. Uses the axiom of choice and all kinds of good stuff, and set theory. Okay, oh dear. This is very, well this is not so bad. Anyway, we're going to see that there's a connection to the proof theory. And I think what I'll do is just postpone this because, again, these things are not looking so great here. But let's just take a look at the first line there. If we're trying to prove A and B, and we're going to do it in a sequent calculus, we might say, well, okay, we're going to do that by the AND rule on the right. And when you do that kind of thing, you generate those two subgoals under there. Prove A, and you get a little thing called the proof of A, and then you prove B, and you get a little thing called the proof of B. And you pair those together and return that pair as the proof of A and B. And you can see how the proof structure actually tells you what kind of evidence you need as you're starting to prove these things in a top-down style. With the existential quantifier, so here's an illustration of what happens, right? You're sticking the proof objects that you created from the subgoals back in. Now with the existential quantifier, you have a pretty interesting demonstration of the constructive character of it. So you want to prove there exists an R of type n, say, such that capital R of n and R holds. You do that by, say, picking a witness, say 0, and then you generate the subgoal with the witness in it, saying, okay, you have to prove R of n and 0. You get the proof for that, and then you go back up in the proof tree and plug it in for the as the witness for the proof part. Okay, so that now let's see how the type theory changes the game and gives us more concepts. So the first concept that you get out of constructive type theory is a very clean account of computability. So we have to have computable, not with respect to Church's thesis, but just the general idea of computability that includes everything we know. It includes a Turing-complete language. Then we have to talk briefly about polymorphism, then uniform validity, and I think we won't have time to do the partial functions. So all the type theories, intuitionistic type theory of Martin-Löf, the Agda type theory, constructive type theory, they're grounded in a computation system. You have to first start with a programming language. We start with the untyped lambda calculus, typically. And by the way, Gödel would be turning over in his grave, right? Because he hated Church's use of the lambda calculus. He thought it was a clumsy, awkward formalism. He didn't believe it was uniform. And when he saw Turing's machines, he said, that's it. That's the definition. So Church made Turing compile the lambda calculus into Turing machines. That was one of the first great results of computer science, when Turing actually compiled the lambda calculus to Turing machines. Anyway, we start with untyped lambda terms, like the one down there, lambda x dot b. That's a value. There are no types on it. It's just what Church was building. And those are considered, that form is irreducible. Its outer operator, lambda, tells you it's a value. You can't reduce it anymore. But what you can do with a lambda is apply it. So you can apply a function there. That app of f to a is the application. And there you have to do some evaluation. And the first thing you do is evaluate f. And you see if it becomes a value, like this lambda. If it doesn't, then the whole computation aborts. But if it becomes a value, lambda x dot b, then you substitute that argument in for the x. Now you can either evaluate it first, that's a call by value substitution. You evaluate a to see if it has a value and substitute it, or you can just call by name. All right, so this computation system is utterly critical to everything that goes on, to the definition of types, to the meaning of the whole language. And by the way, this type theory resolves a big problem that, well, an annoyance in computer science, that there were battles between those people who believed in types and those who didn't. So ALGOL 60 was a typed programming language. Lisp, which is built on the lambda calculus, was untyped. And the two camps fought each other all the time, saying, no, they should have put types into Lisp. And people have done that. But this shows what's really going on. The computation systems there are untyped. That's how computation works. And you put the types on for reasoning. So if you don't need to reason, like if you're in early AI where they were having the computers reason, then you use typeless languages and you just compute away and hope the result is smart. If you're a numerical analyst, you wanted types on everything. Are these reals? Are these floating point numbers? How do I reason about it? So that's the resolution of that old animosity, and it's gone now. People don't fight about that anymore. The other thing about the computation system, though, that maybe goes against what you all think should have been done, is people were worried here about extending computation to distributed systems, to concurrency, and to connecting it to the real world. So we didn't want to adopt Church's thesis. We didn't say this is all the computation, because we will have to hook up with other computers. There'll be communication and that kind of thing that I don't know can be captured. So these are open-ended computation systems. At least the Cornell one was. That wasn't true for Martinov. He was actually, I've been told, I haven't asked him personally about this, but he was toying with the idea of putting Church's thesis in. He wasn't thinking about these extensions. Okay, so now what started to happen is the first hint, whiff of polymorphism, which is key to all this, came from Edinburgh LCF, the guys who showed us all how to automate these type theories. So all of those systems I mentioned, AGDA, HOL, Coq, NuPerl, MetaPerl, they are all based on Robin Milner's Edinburgh LCF way of doing reasoning. And the key to Milner's conception was that the computation system is polymorphic. There are no types on them, what I just explained to you. And the reasoning system should also be polymorphic. So the other thing he did was organize proofs in a top-down way, a tableau-like proof system, because he said, look, you're going to be presented with a goal that you want to try to prove. And the idea is to build the proof by sub-goaling. Say, take that goal, break it into sub-goals, and keep breaking it down. And he built a whole computation mechanism called tactics and tacticals to do that, to make that kind of programming really easy. And that corresponded to the AI approach to problem solving. And in fact, Milner learned this from John McCarthy when he was at Stanford. He learned this is the way AI guys like to think about problem solving. So these are the two things that we learned from him. And so proofs for us look like these trees. They start with a goal at the top, then they break the goal down by adding some hypotheses, H1, and a sub-goal, G1. Then you might have hypotheses H2 and the goal G2 and so forth. So proofs look like this, and the color coding there is sometimes the stuff is trivial. That red stuff, it gets knocked off by decision procedures. The green stuff is what you have to think about. The stars there is when you have to think hard. You got to come up with an idea. But that's the way we think of proof. Big trees like this, the computer filling in lots of bits of the tree. So there's the code, but we won't have time to talk about that. Okay, so let's get a little more into the polymorphism because that's going to be crucial. So the power of the ML organization of tactics is well known, but the other thing that they introduced, this polymorphism, took us a long time to understand how this worked. We have to thank Sergel for this because he brought us a series of unbelievably strong students. So Pavel Naumov came first from Moscow State University, then Alexei Nogin came, who's here, and then Alexei Kopylov. And they all made substantial contributions to the Nuperal system, but the two Alexeis in particular, along with Jason Hickey, pushed this idea of polymorphism. They said this is really very critical. And here's the simplest way to look at it. Let's take a term like lambda x dot x, the identity function in the lambda calculus. That thing is the evidence, the realizer for the proposition A implies A, right? But it's the realizer for A implies A for any proposition A. It doesn't matter what that proposition is. It's a uniform realizer. Works for every proposition. So that's a very key notion. And look at the term just below it there, lambda x, lambda y, pair xy. That's a realizer for A implies B implies A cross A and B. And that works, again, regardless of what A and B are. So this polymorphism appears right away in the logic, in the realizers for propositions, according to the propositions as type semantics that we just looked at. And notice also that this kind of theory doesn't fit into set theory very well. The term lambda x dot x is too big for any set theory, right? It's one term in type theory. In set theory, you have to have the whole class of all sets to be able to get the identity function just on sets. So the polymorphism gives us, is natural, that's the first thing, and second, it gives us these realizers. The third amazing thing it did for us, and this is work of Jason and Alexei Nogin and Alexei Kopylov, they actually were able to use this subtype relation here that says one type A is a subtype of B if all the elements of A are elements of B and if equality of elements in A implies equality in B. And with that, they were able to come up with a really beautiful theory of objects and inheritance. So I won't have time to talk about this, but you can capture the algebraic idea that a group is a subtype of a monoid, which is the way the object-oriented people think about this, by just using this polymorphic semantics. So again, I can't go there because we're running out of time, but they built one of the most impressive accounts of objects and the semantics of programming languages like Java using this polymorphism. Okay, so that's something I won't talk about, but now let's look at the intersection type, which is a key thing. So the intersection type is actually used to build these records and so forth, but it's a very simple type. We say the intersection of two types, A and B, are the elements that belong to both types, to type A and type B, and they're equal in this intersection type only if they're equal in both types A and B. When you use that intersection on families of types, you come up with a type called top, which includes all the terms in the type theory. And I won't talk much about that, but what you have then is every type is a subtype of top. We won't need that in the semantics, but it's a very interesting fact. And I guess I'll have to skip all this. But the cumulative impact was we became very familiar with polymorphism, how to handle it, uniformity, and all this. So what we came to realize, once we were familiar with it, is that the semantics for IFL, intuitionistic first-order logic, The proofs were all uniformly valid. I mentioned that before. But now let's take a very quick run through the proof theory of the first order logic as presented in this top-down style. And you'll see, this is where you'll start to see how the completeness proof works. Okay, so let's take a basic sequence like that one. We've got assumptions, labeled assumptions, A1 to AN. They're all labeled with some identifier, unique identifier. U1 labels A1. So we're just able to refer to the hypotheses. We'll say hypothesis UI, and that'll tell us that we're looking at assumption AI. In general, I write it this way. U bar H means we've got a bunch of hypotheses there. So the axioms look like this. You'll be able to assert under those assumptions that AI is true by just pointing to the variable UI that labels that assumption. So that's how you get axioms. For the rule for implication introduction goes like this. To prove A implies B, you have to assume A, and you want to give that assumption a name. So we're going to write the rule not as implication on the right. I'm going to actually write the rule as a lambda term. The rule is lambda x. And that says, I'm going to build a function. X is the name of the input. So you put the x over there by A. Its type is A. And we got to prove B. To do that, we're going to have to prove, we have to find a term B of x. We don't have it yet, so the lambda term just has a slot for where that's going to go. Once you prove B, you take that, that B of x and stick it into the slot. And the realizer then for that proof is going to be lambda u bar x dot B of x. And that's a uniform realizer, right? There are no types on it. And this is true now for the next rule. So let's look at sample refinement proof now. There's the proof that A implies B implies A. And there's the realizer for it. Now we can do the same thing for, say, implication elimination. Suppose you've got an assumption, A implies B, and you're trying to prove G. Well, the way you can do that is to say, I'm going to apply that function, A implies B, to some argument. I've got to find the argument, so I get a subgoal that says, okay, find me an A. So that's a subgoal. When you get it, you'll have a proof that goes into the slot A up there in the top. And then you get the other subgoal that says you'll now have the hypothesis Y that B is true, and you can use that in proving G. And the realizer you get from this is just G with the application of the function to the argument A substituted for Y. Again, simple and realizable and uniform. So we can do this for all of the rules, and every time after the rule there you see the realizer and you see that it's uniform. Okay, so I won't have time to go through all of those, but you get the idea. Here's the case. We use that term spread to take a pair like this existential quantifier there in the assumption. So we're saying X is an assumption that there exists an X such that R of X holds. That shouldn't be the same X. That's a mistake. It should have been an X prime in the body there. So when you want to use that existential quantifier, you spread it apart to get the element U in the domain, and then some assumption that R of U is true. And you can now use those two pieces in proving G. And again, there you see the uniform realizer. Okay, so that's the story. Here's an interesting thing. If you want to add classical logic, you need the law of excluded middle. And you can produce a realizer for that if you believe in oracle computations. Because there, what you're trying to do is somehow decide, and you need an oracle to do that. This is the only realizer, by the way, that needs the proposition P, because the oracle has to look into the proposition there and say, is that guy true or not? When So this realizer, out of all the ones we gave you, that realizer is not uniformly true. And when you write, if you were to write down the proof term, it would have magic P in it. And that P sits in there and keeps it from being polymorphic. So here's an interesting fact already for classical mathematicians. If you try to give this evidence semantics for classical logic, the only inference rule that goes is P or not P. So you've got another justification why the law of excluded middle isn't the right, well, it isn't uniformly valid anyway. And you're getting uniform validity in the constructive logic. Okay, so now here's the story. Here's the completeness theorem we have. A formula G of minimal first order logic is provable if and only if it's uniformly valid. So you've seen the one half of it, that if it's provable, it's uniformly valid. I'll sketch very quickly in 2 minutes the other side of it. And the corollary, a la Friedman then, is you get the same thing for intuitionistic logic using Friedman's embedding of formulas of intuitionistic logic into minimal logic. Okay, so that's just stating the fact that I just said. So here's how our proof method works. You're actually given the realizer down there. The red thing is the realizer that you've intuited or you've seen by inspecting that formula and showing in type theory somehow or other, you proved in type theory that that is a realizer for the formula above. Now what you do is you call this thing, the combination of the formula and the realizer, an evidence structure. So you've got the formula on one side, the realizer on the other, and you start pushing that realizer into the formula. So you can see right away that we've got a proof coded in here. You say, okay, you're going to use implication introduction, then you're going to use it again, then you're going to spread the hypothesis, then you're going to apply the functions that you got in the spread, and boom, you're going to get the proof out of this. Now that one's trivial. Our undergrads get this once we show them this idea. You can write a realizer down like this and they'll produce the proof. The cool thing you show them is sometimes we give them a formula like not P or not P, and we say find the realizer, and they can't do it. They stare at this, they can't find it. You say, that's why we have proofs, you guys. Go and do the proof of it. That they can do. They grab their proof rules, they run through them, and they find the realizer, and then they get excited. They say, oh, that's why you need proofs. They find you realizers. That's why proofs as programs works, by the way. Sometimes people can't find programs. The way to find them is to state the programming problem as a logic problem. Then do the proof of it, and out will come a program that you never dreamed would happen. And indeed, Chetan Murthy, one of our very famous students, solved an open problem in math, the first constructive proof of Higman's lemma, just this way. He used Friedman's translation, wrote down this thing, gave a constructive proof for it, and out of that proof he got a program. It was a correct program, but nobody in the world could read it. But anyway, it was 40 megabytes long, but it was correct. So this is a methodology here. And now why is it hard? Why did it take Mark and me 2 years to get this to work out? Well, the realizers you put in there can be anything in type theory. So you can use numbers, you can use lists, you can use anything you can think of. You got the realizer, you put it up there against the proposition, and now you try to build a proof out of it. But you've got to, so you encounter a number theory thing. What are you going to do with that? Here's the cool thing that happens. All the uses of number theory, all the uses of list theory, all that stuff must normalize away because this realizer is uniform. So that stuff can't be vital to the proof. So we had to go through a fairly tedious argument to show that as you're pushing any realizer in to build the proof, when you normalize it, all the non-logical stuff has to disappear because that thing has to be a uniform realizer. It has to work for any proposition. So it can't depend on the number theory, the list theory, the type theory you're using. And that argument is fairly subtle and hard, But you can see why the completeness theorem is true here. You're just taking that uniform evidence, building a thing called an evidence structure. And the other cool thing is to do this in general, you end up creating a fan. You create a Brouwer fan. And if Kleene hadn't given us a really nice account of that, we wouldn't have known how to use the fan theorem in this proof. So our proof, by the way, wouldn't work in any of the type theories that used Church's thesis, because the fan theorem and Church's thesis contradict each other, as Kleene showed. So this couldn't be done in AGDA or theories that want to use Church's thesis. Okay.
Thank you, Bob.
Sergel.
Maybe it's a question and a suggestion. Probably it's a convenient time to separate the concerns, because that's unfortunately Bob missed my yesterday lecture, but the talk. But we'll certainly talk about this. There's a computational BHK and there is a probability BHK. They are interlinked ideologically very strongly via BHK semantics, but Kleene made very clear distinction here. The Kleene made it independent or inspired. The Kleene semantic computation was inspired by BHK, but it was the discovery of a computational content of the intuitionistic logic. And this created a huge industry. One of the most success stories in logic, and particularly constructive logic, is the success story. But it shouldn't overshadow. One good success story shouldn't stay on the way of another success story, which you say. And there are certain features which are different, because proofs are not proofs yield programs, but they're not equal. The proof assertions are decidable, realizability assertions are not, and it makes a big difference. So this is a big story, huge success. This is about connecting computations and proofs and computations.
Yeah, that's right.
Yes.
I didn't use the term proof there, but realizers. Because,
realizers, absolutely, yeah. Yes. So this is a great stuff. But also there is another great story which also came from BHK. We may discuss how they interrelated historically, but that's where they speak about really proofs.
Yeah.
And it's a different story. At a certain moment they bifurcate.
Right.
They bifurcate, and one is the one presented here, and the other one really just led to the very generic theory of justifications, which can be just traced back ideologically to Plato. What's a knowledge? Is justified truly? What's a justification? You come with the notion of proof, or at least a proof with a certain with this thing.
Yeah. So I would have been nodding in agreement, and the slogan "proofs as programs" is just short and compact. What should really be said there is the computational content of proofs.
So that's why I'm suggesting this. Yeah. Maybe we should agree upon this, some terminologies, computational BHK and probability BHK. This is my suggestion, but clearly do not insist on that. But there is no any disagreement, because one good thing is always compatible with another good thing.
Yeah.